Yeah. Welcome everyone. Thank you for coming, both online and in person. First talk of the Philosophy of Science seminars run by Bristol Centre of Science and Philosophy of this term. Very pleased to be welcoming Aviram Rosochotsky from Tel Aviv University in the Cohen Institute. Aviram is a PhD student and works on foundations of philosophy of physics, especially in shape dynamics. And he's going to be in Bristol for 2 weeks. If you're interested in learning more about his research, I'll hand over to you, Aviram.
Thanks a lot, Dave.
Oh, this is me.
Sorry about this. So my talk is basically going to be the suggestion that there is a fruitful analogy to be made between preferred time in intrinsic dynamics, also known as the Barbour and Bertotti theory of 1982, and scale in shape dynamics. I'm going to argue that there are several features that are common to both these features, and that in addition, I'm going to argue that the way that we should think about these preferred time and scales is slightly different than the way things usually are understood with regards to theories with gauge, with certain symmetries. And so the structure of my talk is going to be a short introduction to time in classical mechanics. And then I'm going to counterpose this discussion to the status of time, preferred time, and the basic time in intrinsic dynamics. And what I would lastly try and argue with respect to the time parameter, and then maybe draw a similarity with scale, is that I'm going to explain why I think that the time parameter is neither arbitrary nor fixed. So in a sense, it's not an absolute standard, and it's not an arbitrary convention or convenient definition. I would then introduce, to the best of my ability, shape dynamics in very qualitative terms. And then I'm going to indicate, and this is still a work in progress, but I will try and indicate why I think that local scale can be conceptualized in similar terms as being a preferred scale in a very similar sense to the way that time is being preferred. I think that most of my points are inexistent within the literature on shape dynamics and intrinsic dynamics, but I hope that my presentation would be able to flesh out a few of the significant similarities. And so one way to show or explain the special status of time in classical mechanics is to think of classical mechanics as taking place in a configuration space, whose points describe the possible instantaneous configurations of evolving systems of most commonly point particles. And we know that Newton's second law assigns a trajectory to every initial condition that is specified in this space. But in classical mechanics, in Newtonian mechanics, the law of this evolution takes place not in configuration space, but rather in something called extended configuration space. And in this space, the different configurations that a system assumes or can assume also specify the time at which it assumes that particular configuration. And so we see here that we need to add to the coordinates of all of the particles of the configuration an additional configuration which describes the temporal determination or temporal position. And so this structure shows that in a geometrical way that time is being added onto the configuration space in a very clear manner. And this was obviously noted by many physicists and thinkers. One statement by Einstein reads as follows: a non-relativistic theory contains not only statements about things, but also statements which involve things which involve the things and the coordinate systems which serve for their description. And obviously, the classic statement of the status of time in Newtonian mechanics is Newton himself, who characterized the time required by his theory as an absolute, true, and mathematical time. And we can approximately take this to mean that we need to treat time as an independent structure, a determination, in order to come up with an empirically adequate theory. And so in shape dynamics, there is a certain shift away from this conceptual situation. In shape dynamics, it was shown by Barbour and Bertotti that it is possible to describe motion not in extended configuration space, which is Qt, but rather in Q, in configuration space itself. And an additional part of Barbour and Bertotti's study was also to show that one can reduce Q even further onto a subspace of a relational or reduced configuration space, where the configurations are connected only by intrinsic motions. And what this means is going to be specified immediately. And with respect to my talk, there are two questions that need to be addressed here, which are, how is this done? How, just give you a rough idea of the theory as much as I understand myself. And then we would ask what happened to Newton's time. Where did it go? What did it transform it into? Or whether was it entirely eliminated? And I think that the main idea of shape dynamics is encapsulated in the notion of best matching. And best matching suggests a way of decomposing a motion in Euclidean configuration space of classical mechanics onto a component of global translation, global rotation, and intrinsic deformation. And once you have this decomposition in mind, at least qualitatively, then you simply subtract the extrinsic part in order to get the length of a curve in the relational configuration space. And these motions, these intrinsic deformation motions define or live in this relational configuration space that I've mentioned, which is obtained from the Euclidean configuration space by quotiating with the appropriate group of symmetries, which are absolute rotations and translations. And more technically, the way that this is done is by writing down a length or a metric on configuration space and using it in order to arrive through variation at equations of motion, which are equivalent to those of Newton's. And it's not too difficult to show that you can move from standard Lagrangian of Newtonian mechanics onto this description under certain assumptions. And in order to remove the extrinsic motions, one simply has to add generators of these extrinsic motions and then vary them with free end variation. And what this results in is in certain constraints, which are used then to define a subspace of configuration space. And the equations of motion that follow from Jacobi's action is this equation over here, where T is the kinetic energy times 2, and V is the potential interaction between point particles. And the interesting thing about this equation is that it admits a very interesting feature, which is a preferred time parameter. So if we define this function, T of S, and we use it in order to parameterize trajectories in configuration space, then number 2 simplifies drastically to this equation over here, which is just Newton's second law. And in a sense, what this move does is to show us how time emerges in this formalism, the Newtonian time. One way in which this is put is by saying that in intrinsic dynamics, Mach's second principle is implemented by moving from Qt to Q. And in most roughest terms, one can say that Mach's second principle is the idea that motion is abstracted from change. And I'm sorry, time as a previous concept. This is a mistake. And the previous formula shows us in what is the connection between time and change. And in the philosophical literature about intrinsic dynamics, it is often concluded that reparametrization invariance does imply temporal relationism. And so what I want to do in this part of my presentation is to shortly explain in some more detail what is relational about this theory. And just try and identify the different threads or points that are involved here. And I may not have exhausted all of the aspects, but this following list is what I came up with. So one aspect, I think, is the issue of symmetry. The basic time parameter in intrinsic dynamics, which is S and not T, has appropriate symmetries. And why these symmetries are appropriate and what they are, I'm going to explain shortly. A second feature is emergence. Preferred time elapses if and only if motion is taking place. And the way that I think of emergence here is this asymmetrical dependence relation. So we can have change and motion, and this is going to define a time parameter, but it doesn't go the other way around. Time depends on change, but not the other way around. There is a certain hierarchy where time emerges out of a basic formalism, which is in a sense less structured than with the new standard. And so I coined it emergence. And lastly, there is an aspect which I'm not sure how to think of because it does not appear in the classical literature about relationism, but it is also present in the shape dynamics and intrinsic dynamics literature, which I call measurement, which means that the time parameter qua function of velocities and coordinates is quantifying a certain feature of instantaneous configurations. And what this feature is going to be, I'm going to indicate shortly. And so the way I think of it is that the time parameter is interpretable as a quantitative measure. And so one way to see the roles of symmetries, to go back to the first point, is to notice that if time is supposed to be a relational concept, then we would expect it to have no apparent effects. And so one thought experiment found in Barbour states that if we try to speed up the motion of the entire universe along its curve in its configuration space, all motion would be equally affected. And as being within the universe, we could not possibly notice the difference. And so this is a speed up or a slowdown argument in a sense. And the thing is that in Newtonian mechanics, a difference is predicted. So if we take the speeding up of a certain trajectory by a factor of 2, we would find that the forces that are needed in order to drive this trajectory are 4 times as greater. And so here we have a physical difference. And so the philosopher would conclude that if time has a physical consequence, it cannot be relational, but can it? And one way to see how shape dynamics avoids this conclusion very systematically is to carefully note that the basic time parameter in intrinsic dynamics is not T of S, but S. And S has a very large reparametrization group symmetry. We can transform S onto any monotonically rising function of S and still obtain the same trajectory in configuration space. And this is why Barbour and Bertotti say that S is a topological parameter. So distances, lengths, as measured in S, carry no physical significance. And if we speed up things with respect to S, we would obtain what a relationist would anticipate from a relationist theory of motion. So given now that T is a function of S, the transformation of S is going to transform T into T of F of S. And it's not difficult to show that any rate function defined with respect to T is going to transform in this way that you can see before you. And when we when we calculate and trying to find out what the forces required for a speeded up process are going to be, we find that this property assures us that we would need the very same forces. So the implication that we are going to need to strengthen the driving forces in order to obtain a speeded up trajectory is incorrect in this theory, and so we avoid the substantivalist implication. The issue of emergence is also avoided, shown nicely in shape dynamics, because here we can show in explicit terms why time and time elapsing is dependent on change, and it is often noted that one of the problems of Newtonian mechanics is that it implies a time which is independent of change. We can, for example, project a completely stationary universe where particles are not moving in their respective positions. And in the extended configuration space, this is simply means that we have a straight line in configuration space, which assumes different values of a temporal position for different points along this curve. And so, at least conceptually, even if not in practice, Newtonian mechanics does admit the idea of time progressing without any change going on. But with shape dynamics, intrinsic dynamics as a time parameter, we see that the derivative of this time function is dependent on coordinate velocities. And we can see immediately that time is not going to elapse if all of the derivatives with respect to s vanish. We have here an harmonic average of the velocities. And so the mathematical structure of this theory has this very nice feature of showing dependence between time and change, at least in as much as we are speaking about the PTP, the preferred time parameter. And one way in which it was put in the literature is that the rate of change at which a clock ticks is dynamically determined by the distribution of the entire system. I have some qualifications from this quote because I don't think that there is any action at a distance involved that makes clocks run appropriately. But this is still correct if we say instead of clocks, proper clocks. So a proper clock, one which is built to register astronomical time, is determined by the distribution of the entire system, but it's not an action at a distance. It's just a way in which it is suitable or compatible with the desired standard of time. Lastly, the issue of measurement, which I don't have much to say, but it's important to notice that it is there and it is present, is that, as I've said, t as a function of the configuration and the configuration velocities is a measure of the clustering or complexity of the system. And so the older a certain configuration becomes, the richer the structures found in it are. And obviously, the richer the records are, the older the configuration must be. And so we have here a very nice interpretability, as I call it, of the preferred time parameterization, and a measure of the qualitative nature of those configurations, which Julian Barbour calls time capsules. And these are things like an astronomical scale hierarchy, a geological strata, and things of this nature. And now, to get into the second part of this part of my talk, I want to stress that the PTP cannot be conceptualized as arbitrary conventional definition. This is an important point, I think. And what I mean by arbitrary definition is that arbitrary definitions are equivalent with respect to described facts. So we can use this definition or that definition, and no harm would be inflicted on the described facts that the formalism is supposed to represent. And one way in which this was put specifically with respect to time is by the positivist Maurice Schlick, who says that in principle it would be just as possible to define, say, the pulse beat of the Dalai Lama as equal times and use it as a basis of measurement. Only it would be found that this sort of time measurement would be at best impractical and inappropriate for the regulation of clocks. And what I'm going to argue is that this is an understatement. There are better reasons than mere convenience to uphold the preferred time parameter. And these have something to do with the physical description of the system. And so one way that I found, which is very convenient to see this, is by considering the Earth as a clock, and just looking at the history in which astronomers slowly realized that the Earth cannot be used as a proper clock. So suppose we have an effective and heuristic equation which describes the rotational degree of freedom of the Earth, right? So we have here tau, which is a periodic torque, not necessarily periodic, it could actually be aperiodic. We have omega, which is the angular coordinate of the position of the sphere. This is an entirely heuristic equation. I've tried to derive, an intrinsic dynamics with rigid spheres, but I did not have enough time to work that out. So let us just assume that the point particles that are described in intrinsic dynamics give rise to an effective equation for an object which is approximately a rigid sphere. I is the moment of inertia, which we may assume is constant, and f is that function that you may recall, which is a function of positions and velocities of the entire system, of the entire closed system. So we can use this equation in order to define another time parameter, let's call it t prime, and this is defined by requiring that the derivative of the velocity, of the angular velocity of the sphere with respect to t time will vanish. And what this means in practical terms is that we define the Earth to rotate at a constant rate. And so we can use a single revolution as the standard of unit of time, and then we can use things like pendula in order to subdivide the day into smaller pieces of time and then use it as a standard of time. But this has a very, very severe implications with respect to the description of the entire system, right? Because T depends on the torques that are peculiar to the Earth. And what this is going to do is to introduce these torques into the equations of motion of all other objects in the solar system, or even in larger systems if we choose to describe them. And so, for example, if we use this time parameter, we would find that the Jovian or Saturnian systems would appear to accelerate or decelerate without any apparent cause. Or alternatively, if we would like to introduce forces to explain those accelerations and decelerations, we would quickly find that these forces are rather spurious. And what I mean by spurious here is that these forces are not going to be found on Earth, right? Because the Earth rotates at a constant rate. So we are not going to be able to observe them in our immediate neighborhood. They are not going to be related to known properties of matter, right? We know from classical mechanics that matter has properties of inertia and gravitation, and this force is not going to be related to known properties of matter. It is going to be rather an ad hoc addition. And also it would be contradictory to the proven uniformity of the solar system. And what I mean by this is that different pieces of matter distributed in the solar system are of the same kind, they are of the same nature. And so we have empirical grounds to expect that matter in Saturn or Jupiter are not going to exhibit forces that are not known from other parts of the solar system. And so the conclusion I think that one should arrive at is that the PTP is unique and preferred when one considers not only the effects, which are the trajectories of the bodies in the solar system, but also the forces that drive these trajectories. And funny enough, in the 19th century, this was realized, and by astronomers, and when astronomers tried to deal with the irregularities that follow from the changing rotation of the Earth, they came up with the PTP, which is a very interesting coincidence that is observed in the shape dynamics and intrinsic dynamics literature. And what these astronomers did was to solve the Newtonian equations of motion for all major bodies in the solar system. This is step one. And then they would pick a single object, supposedly the moon. Some sources say it's the sun, actually. And they are going to invert the solutions of the position, of the angular position of the moon or the sun, and obtain from the reading of angular position in the celestial sphere the time reading that matches this solution. So if you project the position in the sky of the moon, after you obtain the analytical solution for its position, you will be able to invert the measurements of the right ascension and declination of that particular object, and deduce from it the time parameter that was used to solve simultaneously the equations of motions of all the major bodies. And this allows one to read T from astronomical measurement. And ephemeris time is just this. It's just the measurement of duration in preferred time parameterization. And now I'm getting to the way that we should conceptualize these things. And one way to do so is to notice that even Newton himself had acknowledged that astronomical measurements that aim at correcting irregularities to the rotation of the Earth have a distinct and special status with respect to other standards. And he used the term true time in order to discern these time standards. And in his time, the way that these irregularities were dealt with was with the time equation. And what the time equation is really is just an instruction to the astronomer to add or to subtract from his reading of time in accordance with the solar time, the standard rotation of the Earth, so that the reading would be in line with the average day length throughout the year. So you take an average, the average length of a day to 365 days, and then you find that the average, and in order to correct the measurements per day, sometimes you have to add or subtract a certain amount to get to the corrected time measurements. And you can see that both the mean solar time as measured by the time equation and the ephemeris time, at least in their purpose, they deal with the same kind of irregularities. And even though Newton acknowledged this, he went on to require absolute time. And so I think it's very useful to dwell on this issue for a moment and ask what exactly Newton meant by the term true and apparent and absolute and relative. And so we have three of these dichotomies. We also have mathematical and common. And one way to understand true time is as follows. By true time, Newton means something like privileged, unique, or universal. Although there could be many different apparent times associated with different physical systems, there is only one true time. And I think that you can agree that the preferred time parameterization seems like an adequate candidate to be considered as true time. Absolute time, on the other hand, has some reasonable requirements, but eventually it's also very, very metaphysically elegant. So one feature is that it is insensitive to changes. And what I mean by that, what I think this means is that a minute of running is more or less a minute of walking. And preferred time parameterization has this property. The second feature is changes in the situation of time have no physical effects. And what I take this to mean is that if we translate a certain time interval into the future by a certain amount, then we are going to get qualitatively the same interval, in as much as we are concerned with the time parameter. So we see here a very interesting thing. The PTP in intrinsic dynamics is simultaneously relational and fact-bearing. It describes facts, trajectories, as well as causes, but it is also relational. It is not imposed on us. It is not posited ab initio as a primitive aspect of the theory as it was in Newtonian mechanics. And so one way to state it in Newtonian terms is to say that the PTP is relative and true. So it is a mixed category. And what I mean by that, is there a question? No, okay. One way to see this is to notice that it is not change independent, as we've seen, but it is very well behaved. It is change content insensitive, right? Walking, an hour of walking is the same as an hour of running. The temporal position does not matter. It's part of the symmetry group of the S parameter. And it's also global. We define it for the entire closed system of interacting bodies. And this is actually stated in Barbour and Bertotti's original paper, where they say that these results show that there is no conflict between a fully relational formulation of the dynamical law of the universe and the existence of special frames of reference and special time variables that cast the laws of motion of subsystems on the universe into particularly simple forms. And now what I want to suggest is that something similar may be happening in shape dynamics with respect to scale. So as I've said, this is still a work in progress, and I'm not entirely certain of everything I'm going to say, but I'm going to try and make the best argument that I can. So I'm going to explain to you the simplification scheme that identifies what I think is preferred local scale. And it's slightly more complicated than parameterization simplification, but I'll try to introduce a minimum amount of technicalities. So shape dynamics was developed in the early 2000s, and it was intended to be a generalization of intrinsic dynamics in the case of fields, and principally the metric tensor field that one finds in general relativity. It is a theory in the tradition of geometric dynamics, and what is meant by this is that it takes the space-time continuum and slices it into an evolution of instantaneous three geometries of space. The way that this is done formally is through the ADM decomposition of G mu nu, of GR's metric tensor. And what this decomposition does is to single out the central variable here that is being singled out is Gij, which is the metric of space. And it is accompanied by two other functions, which are the lapse, which describes the separation in time in the chosen foliation, and the shift, which is the component of separation between any two successive points which evolve onto one another in the spatial distance component. And once this decomposition is obtained and substituted into Einstein's field equation, one is going to get geometric dynamics, and I'm going to show you these equations shortly. But what shape dynamics does, to my understanding, is something very similar to what we've seen in intrinsic dynamics. So here we have motion in a space called ring 3, which is the space of all Riemannian 3 matrices. And actually, it could be that the space is not really ring 3, because in shape dynamics, one adds a scale factor and treats it as a non-physical degree of freedom. So this might be a mistake, but the point, I think, is still valid, because you can treat this space as in the same way that you treated the Euclidean configuration space in Newtonian mechanics. And then you can decompose motions of the 3 geometry onto isomorphisms, which do not change the infinitesimal distances between points. Rescaling, which contract or expand in a local fashion the distances, and the remainder component, which is a scaleless geometric dynamics. And this is obtained, again, by generalizing best matching for Lagrangian densities, the same way that we did for Lagrangians in Newtonian mechanics. and one is left with an intrinsic scaleless geometric dynamics. And the configuration space that it is obtained is called shape space. And here we quotient out all of the volume preserving conformal transformations. And this defines this more abstract and reduced configuration space called shape space. So the equations of motion in the ADM formalism, which is very similar to how things are in shape dynamics, looks like this. So you have the main variable of the theory, which is the three matrix Gij, and its conjugate momentum field pi ij. And these two equations are called evolution equations because they can be used in order to evolve a given solution in time. And they are accompanied by two other equations, which are constraint equations. The first equation is the momentum constraint, and the other is the Hamiltonian constraint. And the way to think about constraint equation is that there are conditions on the variables. They usually don't have time derivatives, and for that reason, they cannot be used in order to evolve anything in time. And they also use the compatible initial conditions that you need to work with if you are going to solve the initial value problem. So suppose you want to represent a rotation by a 2x2 matrix, right? You would have too many entrances because a rotation simply requires one angle. So you impose the condition of orthonormality, let's say, and this ties together the different entrances of the matrix and makes it appropriate to represent the rotation. And something similar happens here. So if you take Gij and pi ij, they are redundant. There are connections between their elements that are not present if you simply look at the evolution equation. And the constraint equations tell us how to reduce the number of degrees of freedom implied by Gij and pi ij. And similar occurrence happens in electromagnetism. So in electromagnetism, one has the Faraday and Ampere laws, which are laws used to evolve initial conditions in time. And also there are the Gauss constraint equations, which function the same way as the Hamiltonian and momentum constraint in the geometrodynamic approach. So let me now explain how conformal transformation enter the picture in the context of general relativity, because most of these techniques were developed for general relativity. And for this reason, I think that the best way to present this issue is to introduce it through general relativity. And so this way of solving the initial value problem in GR after one decomposes the metric tensor is called the conformal technique, and it is due mainly to Lichnerowicz-York. And what one does is this. You take an arbitrary metric, Gij, and you multiply it by an arbitrary scale factor, call it phi, and then you substitute it into the constraints. And the constraints result in an equation for phi. And once you solve for phi, you basically have a solution of the constraint equations that you can then substitute into the evolution equations and evolve consistently. So what phi does is to correct the initial guess, Gij, so it will become compatible with GR. Now, in the most general case, the constraints in general relativity lead to a very complicated system. This is because it is not enough to introduce only local scale. You would also have to introduce another correction item, which is sometimes denoted as sigma ij, and then you would get an entire system of equations, which is very complicated. It is called the Lichnerowicz-York system, and it constrains simultaneously both the conformal factor, sigma ij, and the extrinsic curvature. But in intrinsic dynamics, something goes much simpler than that, as we would now see. So in shape dynamics, we trade the freedom to choose arbitrary slicings of space-time to the freedom to choose arbitrary, at least formally arbitrary local scales, so long as they are volume preserving, for an instantaneous hypersurface of space. And this this leads to a very drastic simplification of the constraints. And so the momentum constraint is left unchanged, but the Hamiltonian constraint is split in two. And the remaining system is easily decoupled, as we are going to see. So we can start by solving the momentum constraint using the unimodular gauge, and this is a first step in making the variables ready to be evolved in time, right? And after we obtain this intermediate metric tensor, we can go back and substitute Gij multiplied by an arbitrary factor into the Hamiltonian constraint, which is now much simpler, and it takes the form of the Lichnerowicz-York equation. And one way to put it is that once we are committed to a CMC foliation, this simplification is obtained quite readily. And indeed, the original work by James York was to show that in the special case of CMC foliations, also the constraints in GR are simplified drastically. And what the Lichnerowicz-York equation is going to do is to select a local scale. And this is very interesting. So we have a theory which is it's invariant under conformal transformations, and yet there is a certain calculational device that pushes us towards choosing a specific scale. And so the equation looks like this, and the term on the left is the Laplacian, and this is a elliptic PDE, and it is very well behaved and very well understood. And also, if matter is assumed, and we don't merely deal with pure geometrodynamics, then additional terms appear in this equation, and they show that the scale is going to depend also on the distribution of matter in space. And the coefficients here, as you can see, they are related to the extrinsic curvature, which is used to define the conjugate momentum, and also the spatial curvature. And so, in a sense, what this equation does is to show how the local scale depends on the conformal geometry encoded in our initial choice of the metric tensor. And it is important to realize here that the conformal geometry that Kij and the curvature, they are here representatives of the conformal geometry. What is important about them is the angular data that they encode. So in a sense, what we have here is a dependence between scale and the angular data that is being encoded in a specific representation. So let us try and think about this situation in terms of the three parameters that I've mentioned earlier, which is symmetry, emergent, and measurement. I don't have much to say about measurement, even though I think that there is an analogy also with respect to it, but let me focus on symmetry, please. So we can think of the Lichnerowicz-York preferred scale, as a preferred scale. And it is important to note that in principle, we could choose any scale. So we are not really committed to a fixed or required scale factor. And the way that this manifests mathematically is that we can solve the Lichnerowicz-York equation to obtain the extrinsic curvature, given an arbitrary choice of the scale factor. But the thing is that this might turn out to be very difficult to solve. And so the formalism itself it's as though it pushes us towards a specific simplification scheme, which is why I think that we are dealing here with a preferred scale. So this means, to state it explicitly, that in principle, all scales are allowed, right? But one is preferred. And this is the one that follows if we first assume an arbitrary metric and then derive from it the scale factor rather than the other way around. And it is important to understand the difference between GR and shape dynamics in this respect. So in GR, phi is a correction of a non-solution. So we start with something which is not a model of the theory, and we use phi in order to make it a model of the theory. But in shape dynamics, we have something much more interesting. Phi is fixed, is a fixed representation among kinematically allowed representations. And so we are not exiting the space of the kinematically allowed models. We simply have this constraint, and this constraint acts to guide us into a specific choice of scale. And one way in which this was put by York is by saying that gauge invariance in electromagnetics and conformal invariance in geometrical dynamics are therefore formally similar in several respects as regards the initial value equations. Now, this statement is not agreed upon by the authors of shape dynamics because it seems as though the Lichnerowicz-York equation is going to be interpreted as a gauge constraint. But it's not a gauge constraint. It's just a natural constraint, which is a part of the theory of shape dynamics. And it is important to realize that evolution equations and constraint equations are parts of a single organic whole, if you'd like. It's not as though one just can assign any constraint equations to any evolution equations. Rather, they are both consequences of certain singular Lagrangians, and they describe together, even though they are separate, they describe together a single dynamical idea. But what this quote does show, I think, is that, and is correct, is that in a sense we do have, in the fundamental level of the theory, a symmetry, which allows us to choose any scale factor we wish, at least formally. Now, with regards to emergence, I think by now this might become much clearer, right? And let me read you a statement by Anderson et al., which indicates, I think, very nicely in what way the scale is emergent. So they write, there is a distinguished rescaling of York's TT tensors under conformal transformation. Its use makes it possible to solve the momentum constraint algebraically. You see here how the formalism itself leads us to this kind of approach. And the Hamiltonian constraint reduces to a well-behaved elliptic scalar equation for the conformal factor, the Lichnerowicz-York equation. Because this is to be solved for the conformal factor, the original three-metric Gij turns out to be unphysical. But the physical three-metric phi Gij is deduced by solving for the conformal factor. So one way I think that we can conceptualize this is by using Newton's distinction and differentiate between true and absolute scale. And so with this vocabulary at hand, we can explain a few things about the status of scale in shape dynamics. So we know that things in nature have natural scales, right? The sun is bigger than the planets. And so we have to make compatible the impression that there are natural scales in reality with a theory which is scale invariant. And one way to do this is to use Newton's terminology and say that the universe's scale hierarchy is true. It is built out of the dynamical entities of the universe and the laws that describe their motion, but it is not absolute. The formalism itself allows us to choose any scale we'd like, even though it prefers one scale. And so it shows us that scale is not imposed as an external structure or an independent structure, as it would be if the equations would have required a specific scale in an absolute sense. So let me suggest a few conclusions that I draw from this discussion. Usually, when we think about gauge freedom, then there are two options. One could use gauge reduction, which is taking the quotient of the configuration space with respect to gauge transformation, and then just completely forget about the broader structure. And another approach is to take a gauge constraint, an arbitrary gauge constraint, and simply work within one subspace, which is convenient within the larger space of representation. But you see, I think that theories with preferred representations, they fit neither of these approach, right? And so this suggests that something like an emergent relationism may be needed. And this term I got from Karim, and I think it's pretty good to describe what we are aiming here, because you see, shape dynamics in a sense, it eats the cake and keeps it too. I mean, we have this conformal transformation symmetry, and also we have a preferred scale, which gives content and satisfies our requirement of having natural scales in nature. And another conclusion that I want to suggest is that mathematical representations should be evaluated not only kinematically, the way that the positivists thought of it, in terms of the instantaneous position or value of a certain physical variable. We should also look at causes and ask whether a certain representation is adequate with respect to them as well. And I think that the true apparent dichotomy is quite good for this purpose. I think that one can redefine true and apparent by saying that it means compatible or incompatible with all aspects of matter. So we are not omitting anything when we choose a true standard. The relational nature of these enterprises is preserved so long as we show that we are not dealing with anything which is absolute, independent of matter. There are several open questions that I'm still thinking about. And I would like to hear what you have in mind about this. And the first question is whether the preferred scale can be thought of as characterizing an instantaneous configuration in the same way that the PTP does. So if we think of the scale of Lichnerowicz-York scale, which is a function of Gij, Πij, and X, we would like to ask whether it quantifies a certain qualitative feature. And if so, what is this? And there are indications in the literature that this is the case, but I just haven't got to read about this sufficiently enough to include it here. There is also the question of what is analogous to forces in intrinsic dynamics with respect to scale in shape dynamics. So my original argument showed that if we want to describe forces as well, we cannot say that the PTP is an arbitrary convention. So what would be analogous to forces in shape dynamics? I still haven't thought about this significantly, but it seems to me that one way to approach this is by noting that curvature is not disconnected from scale. And so if we choose arbitrary scale, we are going to create, maybe that's one way to call it, apparent curvature, right? So, and if we have this apparent curvature, which is not caused by any sources of curvature, then we could say that maybe we could say that this can disqualify on a causal basis non-standard, non-preferred scale factors. And also there are still technical questions that I need to be convinced of myself in future work. And this is to determine how strongly are arbitrary scales prohibited by the formalism. As you've seen, the procedure requires a unimodular gauge, and it also requires a certain sequence where one first solves the momentum constraint, and then one moves to the Hamiltonian constraint, and this leads to the Lichnerowicz-York equation, which picks out scale. But the question is, how difficult really is it to solve it the other way around and assume an arbitrary scale and then later on solve the momentum constraint? So what I want to be certain of there is that there is a true directionality in the way that the calculations should work for me to be able to claim that really we have here a preferred scale. So this is just what I've said, and that's it.
Thanks so much, Aviram, for that really great talk. We'll take a 5-minute break so people can go to the toilet or get a drink. Or maybe 3 minutes now. So we can rearrange it at 6 o'clock.
Yeah.
Cool.
I'm not gonna grab my jacket. It's cold, isn't it? Yeah, surprising. You can just stop share.
How do I do that?
Press stop share.
Pause.
Let me do it.
It's okay. Oh, you also
No.
stop the recording.